Welcome back to lectures on artificial neural networks. Today we will discuss what a simple neural network can do for you, basically, and what are the capabilities. So let's start with just a simple neuron and see what happens. So the title of the lecture would be what a simple neural networks can do for you or for us. All right, let's see. So a simple neuron, basically, let's say it has a state of V sub, let's say J, is one of the neurons, and then it receives input from the outside, and for simplicity, let's say we have only two inputs, so that would be V1 and V2. So they're connected through the weight factor W1J and W2J. All right, so as we discussed previously, we have the state of the neuron, V sub j, is equal to either 1 or 0. You're in active state or you're in inactive state. Now, how that is decided? Depending on the linear combination of the input received. So, in other words, we have basically W1j times V1 plus W2j times V2. It should be greater or equal to some threshold value showing by T sub j. Otherwise, the state of the neuron would be at 0. So this would be otherwise. All right, so let's see what this means. What does it do for us? One of the important applications of what we are really after is for basically pattern recognition, decision makings, and tasks similar to those. So let's see what just a simple neuron works as a decision maker, because we have a inequality here, so it gives us an idea that this is a decision maker. Depending on the threshold which is embedded in the neuron, we can have a decision. So what type of a decision making this neuron does, if we look at the boundary of the decision, is when we use the equal sign. So the boundary of decision is basically where we have W1j V1 plus W2j V2 equal to T sub j. Now we can rewrite that in more familiar form as W1j V1 plus W2j V2 minus Tj equal to 0. Now, if you look at this in the space of the input, which is V2 versus V1, we can see this is just the equation of a simple line. So this simple line could be as this. So this line is basically described by this simple equation. Now, this equation here, we see that this line is basically dividing the regions into two parts. One region would be when we have bigger than the threshold, and normally we put a little arrow here identifying that this is the region when we're dealing bigger than 0 or the threshold. And the other region naturally would be when we're dealing with the less than the threshold. So when we are right on the line, we're dealing with the equal to the threshold. So we can see that basically the neuron is dividing the regions into two. So when we are bigger than the threshold, then the state of the neuron, Vj, would be equal to 1. When we are less than the threshold, the state of the neuron, Vj, would be equal to 0, basically. So that's basically what a simple neuron does. Now, depending on how you decide on the weight factors and also the threshold, this line basically can move and put itself to anywhere that we desire. So let's just make an example, see what we can, accomplish with this. A good example of that would be, so this would be an example, would be, let's say, an OR gate. Let's say you want to implement an OR gate using this simple neuron. So an OR gate, the truth table for the OR gate is V1, V2, and let's say V3 is the output. So if you have 0, 0, we have 0 output, and if it's 1, 0, it would be 1. If it's 0, 1, it would be 1, and if it's 1 and 1, also the output to be 1. So let's just put these points on the input space that we have. All right, so the first sample that you have, it says 0, 0, the output should be 0, and I'm showing it by basically a circle. And if I have V1, 1, V2, 0, then we would like to have 1. So let's say this is shown by cross, and the other point would be on the vertical axis, is also shown by cross. And then the last one would be 1 and 1, which would be this point here, showing it by cross. So what we want to do to implement an OR gate, that this is basically the symbol they normally use. So this is V3, this is V1, and this is V2. And what we need to have is basically a line, a simple line, dividing these 3 points from this single point. So one particular example could be this simple line, which goes through 0.5 here, and it turns this side to be positive. So then the output is equal to 1. And if you are on this side of the line, V3 would be equal to 0. So this will implement the OR gate. Now let's figure out what are the weights that can accomplish this line. So the first thing is to write the equation of the line, see what that equation is. So equation of this line, simply from what we have known before, is it could be V1 plus V2 minus 0.5 equal to 0. This equation basically represents this line. Now, this is not the only equation. You can multiply the equation by any constant to be positive or negative. It does not change the line. So in other words, there are many solutions to this neural net. We're taking the simplest one here. Now, let's check to see if this represents the inequality that we have. So to check that, you have to check a point which is not on the line, on the boundary, and then to see whether the inequality is positive or negative and which one is represented. So if I choose 0 here, 0, 0 for V1 and V2, we can see substituting 0 and 0, you get negative 0.5. So it means you are on the negative side, and that's what we like to have, which gives us V3 equal to 0. And this side V3 equal to 1. So this equation works. So for that equation, then we can see, if you compare this equation basically with the original equation, you can see what are the values of the weights and the thresholds. So in this case, we have V1, 3 equal to 1, W23 equal to 1, and T3, the threshold, equal to plus 0.5. So the neural net that we have here then would be a simple neuron. The state is V3, and the input going to it is V1 and V2. And the weight factors on these would be simply +1, +1. And the threshold here, T3, normally they write it underneath the neurons or within the neuron, is equal to 0.5. And that will basically represents a simple OR gate. So this is what we have here, is implementing what we have here. Now, just comparing these two units here, this is the ordinary logic gate, and this is what is called threshold logic gate. And you can immediately realize that the capability of the threshold logic gate maybe is a little bit more than the ordinary logic gate, because the logic gate is stick to the truth table, and this is all it can do, is very crisp and rigid. But the threshold logic gate has more flexibilities. And you can see the flexibility is that any points represented on this side of the region gives you the output equal to 1, and doesn't have to be these points. It could be, infinite number of points on that side, and any point on this side which gives you 0, basically. So this simple lecture gives you an idea that what a simple neuron with 2 inputs can do for you. And we will see that what are the capabilities in other lectures, that we have more complicated set of neurons, and then we will see what happens.